Okay, I found that I was mute, right? So I guess I need to start again. So okay, um, we are going to talk about conflict today. So we talk about like uh, new letter last time. And this, oh, by the way, this is the last class. Like we don't have any classes next week during that week. And so this, of course, it will be just an overview like today, like for conflict, because we just have one class for this one. But I have another course on neurolaters. Some some of you also taken this class or like taken that class or like taking that class at the same time. So if you are interested in this kind of materials, you can consider taking that. Like I should offer that again next spring. So so anyway, like conf that is basically short for convolutional neural network. Neural net. And and so as you understand, like okay, what we talked about last time for neural networks, like typically a neural network is arranged in layers. And also if you remember, like we can have an input, for example, input image here. So you can consider the lower layer is trying to extract some of the lower level features. And then you have like middle layer, maybe middle layer level features, and then like in the later layer and is doing the actual job, doing, for example, classification and regression and so on. Um, and um, and okay, so neural networks by itself, okay, it works. When we talk about like neural networks, like last time, typically we are considering fully connected layer. So so what I mean is like we have, oops, we have something like this. Like if I have an input here, I have a nuance here. So the neuron is connected to every pixels of the input. Um, the problem is like this is typically very expensive to compute, right? This contain lots of parameters. Um, so probably it makes sense to just do a uh, kind of like sparse intersection. For example, you can consider like in the next layer here, you have each new one. It just correspond to a local region of like just here. And this new one just responds to here. So therefore, you don't need to connect this one to every pixels, but just over here. Now, this reduces some of this computation already. And but there's still like lots of parameters. Like it reduces significantly the amount of parameters. For example, if I start with like this image is like maybe 1,000 by 1,000 pixels here, and then let's say I have here like seeing here say maybe in the middle layer I have like 100 by 100 neurons here. So now if I reduce this filter originally, if I am doing so maybe like this hidden unit is like 100 by 100, let's say. Now, if I am doing, oh, okay, maybe like it's good to pause. Like, so therefore, like how many parameters if we have for the original NLP, like for original multi-layer or like original little fully connected layer. So from this layer to this layer here, how many, if I'm doing fully connected layer, how many parameters are here approximately? Yes, yeah. So you will be just like multiply them together, right? So the number of parameters. Now, if I kind of like reduce that, as I mentioned, okay, I don't need to have like this one, each of the new one connect to like every pixels in this image here. Maybe I can reduce the reception fields to like just 10 by 10 here. So then maybe this is like a question two here. So if I reduce the reception field, say for each of the filters just 10 by 10. So now how many parameters are there now? So but you guys are still answering the first question. Maybe you probably want to put like Q2 or something like if you for this one. Yes. So you all get the points, right? So now, and I can even reduce further, like the number of parameters. The thing is, like, if you think of like each of these new ones, I am moving around. Okay, this new one represent for this region, this new one represent for this region. But to begin with, like, um, there's no good reason that like um the new one here should kind of like uh behave differently for new one here, right? Because you think of an image here, after image like this one, but I may have my target shifted here also, right? I shifted here. Maybe I do not draw here. Maybe shifted here. So there's no good reason like why pixel here, like around this region here, should behave differently, like for regions here, and also everywhere else like in the image. Maybe honestly, maybe that can be because if you consider the image you're taking care of is always have the targets in the middle. If you are okay, I don't know who is yeah. So um then but anyway, like in general, like there's no good reason to do that. So then we can just assume like all these filter behave the same. So we can share the weight essentially. So each of them like have the same weights here. Now then the number of parameters will further reduce significantly. So oh okay, maybe I still ask you. So what if like I share parameters, number of parameter if we share this is so in this first layer, like original the image of like 10, like 1,000 by 1,000, and then like in the second layer, I have 100 by 100, like second layer. Now the question is like if I okay, I'm doing CNN now. This is basically CNN is what? Basically CNN is like I have a limited reception field, and also I share the parameters across all the new ones for the CNN layer. So now if I share, okay, this is actually a very silly question. I just want to see if you guys are following. So if I have all these I share the same parameters here, now how many parameters do I have like uh for this layer here? Uh, you are saying the second Alison, your question is like for the second question or the third question. For okay, if you share them, um, so you all of these nodes will be sharing same parameters. Basically, you can think of like all of them, or all having like the filter is like 10 by 10 here. So all of these parameters are the same. So yeah, okay. For cell, if like it's 1,000 by 1,000, that would be like the second one. If like I if I don't share the parameters, then like they will be all the same, right? Sorry, we don't share the parameters, then they all will all be different. So therefore, like will be each of the new one will have like 10 by 10 so many parameters, and so I have like 100 by 100 new ones, so I have like 1,000 by 1,000, right? So but for a typical CNN layer, what's going on is like I will assume like each of the new ones in the layer will share the same parameters. So therefore, like since they share the same parameters, they are all the same. So I will just have like for each of the new one I have 10 by 10 here, but all of them are the same, right? So therefore, it's actually really just a 10 by 10. So many. So you see, like that's a significant. Like if I summarize that, like we start with like 100 by 100 by 1,000 by 1,000. So if I reduce the reception field, I have like 100 by 100 by 10 by 10, right? And if I further like share the parameters, I will just have 10 by 10. And this is basically the CNN layer. So the CNN layer is nothing. It's just like you doing this kind of like um weight sharing, and also like doing a limited reception field. So um and that's it. Basically, that's it. So this is I guess like this major take home message. So when people talk about CNN, it's nothing really fancy, but it's really like if you do fully connected layer, you have lots of parameters and also lots of computations. So we want to reduce that. Then you try to share the parameters and you try to limit the reception fields. So that becomes a CNN layer. Yeah, that's just summarizing what I mentioned. So this is a illustration here again. So I have like all these new ones now in the hidden layer. You see like they have like a limited reception fields, and all of them are sharing the same parameters. And this is a example like okay, that you saw this slide before like long times ago. So if you think of that like when they have a finite reception field, and what they do like for CNN or like in general for neural ledgers, the linear layer is like just you have the weight here, you're doing weighted sum with the input here, right? And this operation is essentially is basically just like doing correlation, right? Or like you can think of correlation and convolution are essentially the same thing nowadays. If you're not single processing people, if especially if a machine learning people, they essentially just think of like convolution is the same as correlation. Then this is really like for each of the filter, you have the weight here is a, like as a patch here. You're just doing inner product with this one here, right? So it's essentially totally the same as what we had before, like doing a convolutional filter or like correlation more precisely. So you have a filter here, you just like do a inner product, like you take a patch like for the image and you do an inner product like for each patch of the image. Now the only difference now here is that in conventional, like in computation, classical computation, or like deep learning computation, we talk about whenever we talk about like convolutional filter, like correlation filter, the filter is a is uh, designed beforehand. So you have like some way to design that, maybe wavelet filter, like a Bohr filter, so on and so forth. But in CNN, in neural networks, those filters are data driven. You have like the data given to you for the problem, then you are trying to train the filter so that that filter work well with your problem. So and this okay, this is again I just re-illustrate the things again. Right? We have this WE sensor filter, then also like typically you include bias here, right? Then okay, this is essentially what's going on for the filter, right? So here is they have this so-called perception. Oh, okay, we mentioned perception again, like earlier. Did I? I forgot. So, but perception is just like the old names, like when you have the activation function is like a step function. So if you remember, like from last class there, like we have a artificial neurons is you have like input like coming in and you do weight the sum here. Actually you typically you can also add a bias here, but your bias can also absorb into here. And after you do a weighted sum, then you go for a uh, activation function. So this activation function like can be sigmoid, can be valued, and so on, and give you an output, right? So this is like the operation of artificial neuron, and this part is essentially just this one here, right? Doing the inner product with your weight parameters here. And then if your activation function here is like doing a step function, then historically people would call this as perceptron. But nowadays, like people say like multi-layer perceptron, even for cases when your activation are not actually a step function. And yeah, it's a kind of a misnomer, but people just um, yeah. Um, yeah, I mean like this yeah, it's just I mean like it's used like in this way anyway. So yeah. And okay, this is another illustration. I have lots of illustration here. Like you do the convolution, so it's just like this way. Now, okay, that's a some terminology here. There's if you go into like deep learning or like neural network or like Python packages to implement neural networks. Uh, for the CNN layers, typically there's a parameters along a stride. So there's nothing, it's just the skip step. Like how are you going to just like take every, okay, like for example, like earlier, this is like stride one here, you just have like uh, go one step at a time, right? So when we say stride two, for example, like let's see, stride three, you're just going to like, I will skip like two, three step at one time. So this is stride three, or like you can stride two or whatever. So and this is about stride, and then like another thing like people may need to consider is like the boundary condition. For example, like here, if I start with the image is 32 by 32, and then let's say I have three channel here by three here. Okay, this is another thing, like it's a little bit different. Um, kind of like conventional, by convention is a little bit different from like classic uh, kind of like image processing, the filter image processing. Typically, when we do like filter like in image processing, when we have an RGB image, let's say, so we have three different channels, right? Typically, we will have like three different filters and add on this channel, like each of the separate channel. But in CNN, typically we will take the entire image. In this case, would be like a three-dimensional object here. So therefore, like here, I have like 32 by 32 by 3 here. So now when I do a convolutional filter, I'll just take a block here. So it's like, for example, I have a filter, it's like 5 by 5 by 3. I'll have this block here, just directly do an inner product with like a block extracted from this three-dimensional object here. So then so if I have the filter, it's like 5 by 5 by 3, assuming I don't do any padding. So what I mean by padding is I add something at the boundary. So if I don't do that, then the dimension, the maximum dimension, or like the reasonable dimension for that will become 28 by 28, right? So because I can start from, okay, what I mean is I have like here, this one is 32 by 32, right? So if I have the filter is 3 by 3 here, so the first pixel, let's say I index this pixel here, 1, 1 here, right? The last one is like 32 by 32, right? So I can only center my filter starting from 2, 2, right? And I can only end my filters ending at like 31, 30 by 31. Oh, sorry, like my filter is 5 by 5, by the way. So it's 5 by 5, then I have, I can only center my filter. Okay, I guess like one of you guys probably want to mute your, I don't know, like why, uh, uh, yeah, okay, anyway. So, uh, so if I have my filters 5, 5 here, I can only start the center of the filter pixels start at like 50, something like that, right? And end at like, let's say 29 by 29. No, sorry, 30 by 30. So okay, anyway, so therefore from 50 to 30 by 30, that would be like 28 by 28. So okay, maybe another question, just make sure you guys are following me. So how about if I have a filter 7 by 7 by 3 here? So what is the output dimension? Or actually, I shouldn't say 7 by 7 by 3. I should say the filter size is 7 by 7. What will be the output dimension? Okay, I should remove this one. This is a bit confusing. So is that clear? So if I so yeah, we can do some counting here. So if it's 7 by 7, like it can start from, so I actually like 7 by 7, the center is like, actually you can think of like a remove boundary by 3 from each of the edges, right? From each of the boundaries, right? So like it should be like 32 by minus 3 times 2, something like that, for each of the edge. So therefore it's a, what's that? 26, right? 26 by 26, something like that. Um, okay, I just erase this one here because I typically like when we typically we don't just use one filter here. So we will have multiple filters and we represent it, like we will put it in stack. For example, like we will say I have like 6 5 by 5 filters here. Then after the conv layer, then I have a 3-dimensional object, say from starting from 32 by 30 by 3, it become like 28 by 28 by 6. So so therefore when you see people like write like you have a conv layer, let's say like 5 by 5 by 6 is like typically meaning that like I have the kernel size is 5 by 5, I have 6 filters for that. And afterward, like so therefore I should have like 6 channels like after the filter as well. And my dimension will kind of like go down or whatever. So but oh, actually, anyway, I don't mention padding here. Maybe one word here is like here I don't consider padding, but that's oftentimes like you can also impose padding. Like for example, like uh if you know okay, maybe I mentioned a couple packages like to do neural networks, very popular one. Probably like okay, maybe like okay, a participation question like probably many people knows, but maybe many of you guys don't know. So how many of you like heard of TensorFlow? Just yes or no? Okay. So some of you yes, some of you know. So TensorFlow is a very it's good you know TensorFlow. I mean like at least heard of TensorFlow. Um because it's extremely popular, it would be very helpful if you go to find a job or something because I honestly I also like since you guys are going to graduate very soon, I think like you guys should invest. Well, of course you play with Python a lot already, like in this class. Yeah, Python is very useful nowadays, like because you you maybe JavaScript. I don't know. I'm a bit biased because I don't know JavaScript. I mean, I know JavaScript, but I don't really actively write any JavaScript stuff. So, but I cannot think of like another language like more important than these two in practice. So uh and especially if you say you do machine learning, deep learning, I'm kind of interested in AI and so on. Like it's very useful to learn Python because like if you think of like all these free packages that allow you to build like machine learning models all have like API in Python. Like even like, many of them like develop like completely like targeted to Python. So TensorFlow is like one from Google. It's getting very popular now. Is you can use that like to build like new lateral as I mentioned last time. Like I guess at the end I mentioned okay we can write a very simple code to build a simple neural networks right with like 25 lines of code or something like that. But if you try to build a bigger neural network, say, it's become more and more complicated to write your own kind of like code from scratch. In particular, like for example, you have like if you remember, we do backpropagation, right? If you write code from scratch, meaning that like basically you need to do all this calculus yourself, like for each of the uh, computational node, you need to compute like write the code. I basically compute like okay, what is the local gradient for this guy and how the backpropagation is done. But with this package, you say many of these steps will be like kind of like simplified significantly. They will be performed like automatically. Um, so TensorFlow is by Google. That's another one is like very popular is PyTorch. So it's like kind of like a follow up of Torch, like it's like originally in the language Lua, then it kind of like port to Python. I think it's maintained by Facebook. Um, and TensorFlow also like has a layer, kind of a simplified layer for TensorFlow, or like you can think of like a layer to uh, make it more high level. So it's a Keras. Like now it's also maintained by Google as well, because the creator was hired by Google. Um, yeah, I guess I personally I like PyTorch, or like at least I got my familiar with PyTorch. No, actually no. All these are in for MATLAB. Like they have its own stuff, but I highly not recommend like playing with MATLAB, both because it's expensive and also like for the people, like if you look at like paper, like most of them will actually like, will use this. Like MATLAB is like not in the mainstream basically. Um, there's like several MATLAB packages. If you just like pay for fun, like I forgot like there's a yeah I forgot. Okay, of course MATLAB itself it has some deep learning library there, but the packages are definitely you need to pay for them. I believe it should be expensive. Um, yes. What else? Oh, okay. Yeah, I'm here. Okay, okay. Sorry. I'm stretching too far. So, um, yeah, or you can pay with like either Keras, PyTorch. I also have like several like high level layer like on top of that. Like that's one. Okay, that's one like now getting pretty popular. It's like PyTorch Lightning. I don't have time to pay with it myself yet. But uh, you I don't know. I probably the PyTorch itself is simple enough, or you can look for Keras, like start with Keras basically. But what I want to say is like, for a CNN layer, like you also have like I did mention padding, like we mentioned stride here. Right? Stride is just the skip step. Padding is like just, for example, if I want to get this like the same dimension as before, then I can pad some zeros here, right? For example, like I have like 32 by 32. Maybe I can pad like two lines of zeros across like each of the boundaries there become like 35 36 by 36, and then I do the conf layer here, I will get back to have like 32 by 32, right? So then you can have padding of 1, 2, or 0, or so on. So for example, in this case, if I want to have the same dimension as before, I would like to pad like padding is equal to 2, something like that. So, and in PyTorch, right, you need to specify the padding like precisely numerically. But in Keras, I know you can do this called same padding. When they call same padding, you have the dimension of the output is the same as the input. Yeah, but yeah, this is just something minor anyway. So this is about padding and stride again. So and another layer like you will often encounter in
Dr.
CNN.
Chen,
Yes,
can I ask a question?
yes, sure.
So in this slide, so after the one convolution, so the width becomes 6, right? From 3 to 6, because you use the 6 filters.
Yes, yes.
So then how these 6 layers corresponds to RGB?
Oh, no,
Because,
cannot actually, because when you have the filter here, you have the each of the filters say like you process like a block, entire block, for example, like 5 by 5 by 3, this block here, just do an inner product with a patch with a block here, right? So all these RGB component mix up. And also remember this filter itself, like you train it, you don't design it. So therefore, like this will basically all mix up. Like for each
I
of
see.
this representation here, you cannot really distinguish like what is RG and B and so on. Yeah.
I see. I
Yeah.
see. Okay. Thank you.
Sure. So and then okay, yeah. As I mentioned, like okay, that's another layer like you encounter often in CNN is a so-called pooling. It's a very simple concept. It's just like trying to reduce the dimension. So the most popular pooling is the mass pooling. For example, like if I have this is a particular patch here, so I have this something like this. I can have like a 2 by 2 pooling, mass pooling with stride 2. Then is what it does is I take a patch here and compute the maximum. It will get me this thing here, and then compute another and move to another patch and compute and we get this one here. Um, and it's popular. It's actually it's common that like when you have a pooling, like for example 3 by 3, you have like strike 3, 4 by 4, you get strike you use strike 4, something like that. But this is not a um, this is not a must. You can also like say like 4 by 4, I might do strike 2. This is also possible. Like, but it's much less common, I guess. But this is like just pulling, and then like essentially like okay. I'm also like one thing like people may do is like you may do some normalization. So for example, like think of like for image like this, I may have a different contrast, then I still expect that the response is the same. So what we can do is like we can just do a normalization before putting uh, into the network. So the normalization can be just like subtract the mean and then like over the variance, over the standard deviation, something like, yeah. Yeah, this is a definitely an error here. This is a the standard deviation. Right? So I just yeah. Anyway, that's the problem like with using other people's slide directly. So anyway, and then okay, yeah, then like we go for the conf layer here, and then we go for the pooling here, and we mention this normalization here. And maybe just like a quick word also, like this normalization here, this local contrast normalization. Honestly, I don't think it's very popular now. because um, or I shouldn't say it's not popular, but in the sense that people did it, like still did it. But it's like did it like by default already. Like when this is like automatically done, that like people usually not aware of that. Um, and uh, and here like when we call this when they refer this one local contrast like normalization, typically only doing do this like at the beginning like to the input, but oftentimes like, we can also do normalization in the middle of the lateral. For example, if I have a let's see if I have an example here that I can like for example like if I have lateral here like have multiple layer of laterals, right? So after each of the convolutional layer or like at the beginning of the convolutional layer, I may do a normalization again. Oh, actually, typically I should do the normalization inside the convol. If you think of the convolutional layer, it's like the weighted sum of the real one, and then I go for the activation function. So the activation function here. So we may do a normalization after the weighted sum and trying to before you're going through the activation. Uh, so because if you think of like, for example, the activation function is a sigma here, right? Something like that. So you may want to operate near this linear region somehow. You don't want to saturate, like always saturate somehow, right? So then we may want to do a normalization here before you get to the activation function. So and sometimes you see like people in the this kind of deep learning and neural network literature, they always mention like how to they perform this batch norm here. That's precisely the normalization they refer to. So when they say batch norm, it's like because you train the model in batches. So then they normalize to the mean of the batch. Basically, you take the compute the mean of the batch and compute the variance of the batch, and then you normalize according to the batch mean and batch variance. You can also like not do the normalization based on the statistics of a batch, but you statistics of a layer or statistics of a group. So therefore, you also see people call a batch norm, a layer norm, and like group norm, and so on. And also another remark for this batch norm here is that like it's often like when you do batch norm, you also like not just normalize that. You can also like after normalization, you add a bias. Where is that? You and also actually typically I guess it's like you can also scale it and then add a bias as well. This is a multiplication, scale and bias. So the meaning is that like the of this the purpose of this scaling and bias that like you're not sure this normalization. This I said I have a normalization here. You're not sure this normalization is also always helping. If actually you really want to operate in this region rather than this region, then you always force your input to this like activation function like in this region may hurt you rather than help you. So then in this case it's like maybe what we can do again is like we just let the data to teach us what we should do. So then we will just add back add back a bias and multiply by scaling factor here. But these factors also will be learned rather than like just pre-design. So we will just learn from the data whether we should add back a bias or like add back how much bias or like multiply by what scaling factor here. And so this is batch norm and all these other normalization. So and yes. Okay. Uh, so then like as you can see, this is the common structure for at least for the most popular like even though like nowadays has lots of refinement, but the classic like conflict, you will see something like that. Like you have some conf layer here, and then you do pooling, and then conf layer here, pooling, conf layer pooling, and so on. Like each time you do pooling, you do a downsampling, right? So if you look at that dimension here, like you have the input, like let's say, it's like 75. Okay, like by 4 here, this is okay. Let's see if I have like something. Maybe this one is a better example. More so maybe I have like more lateral image here, like about 200 by 200 by 3 channels here. Now I do a conf layer conf filter like 11 by 11, and I have 96 filter here. You see like that become a block. It's like 55 by 55 by 96. So it do a stripe for, you see it reduce the dimension quite a bit. Now it do a mass pooling, so get like further mass pooling of stripe to further reduce dimension to 27 by 27. And I'm not sure this figure is a, okay, yeah. I think like then it's, oh, okay. I guess this mass pooling and the filter itself I put together like here in this block here. And then like it also do another filter here, like 256 filter, then like you have like this dimension become 27 by 256. Then it reduce the dimension again, like using like mass pooling, then to 13 by 13 something. Then you add like uh 86 84 filters, then you get something like that. So typically you go, the dimension go down a bit, and then you get more and more channels, and then eventually like you get a object of size like this, and then you go for like several like a fully connected layer, and then like this you get whatever. Okay, this is like the AlexNet, as you remember. I don't know whether I mentioned this last time. So this is like the winning. I guess I mentioned that winning the 2012 like ImageNet competition, right? So it's like doing this classification of like uh, classification challenge with like 1,000 classes. So you have 1,000 objects here, right? So then the last layer, you see like it have like a a factor of like 1,000. So each of them will be a score here. The largest score will be like the largest score will be the winning class basically. So and this okay, this is just okay. Um so I mentioned some of this example already last time. I guess I guess so um if we do classification, of course I don't know, like because I have 30 minutes, I'm I'm thinking like how I should spend with time, like um so okay, and maybe I will first like do a demo first, and then like if I have a bit more time, then I will I'll explain a little bit, like for example for object detection or like for segmentation, because you see like for classification the problem is will be the solution is quite apparent, right? You have this telescope like laterals, you get like the dimension is smaller and smaller and channel more and more, and then you eventually have like several fully connected layer, and to have like, let's say if you do classification of 1,000 class, then you into a vector of like 1,000. But say if you are trying to do a segmentation, or like trying to do like semantic segmentation, as like this one here, for example, I want to segment the whole image, or like I'm trying to do this kind of semantic segmentation. So I'm trying to see, okay, uh, this is basically color for building, and this is color for the door, and so on. Like for example, like I will segment, oh, this is like for the wall, this is building, and this is sky, let's say. Then Okay, by the way, this is known as semantic segmentation. Like for each of the pixel, you can try to classify into like what object it belongs to. And I mean, this case, this is a classification problem, but it's a dense classification problem, right? For each of the pixel, I'm going to get a class. It's not like the entire image, I'll get a class. So then in this case, I need to get back uh, really the output of my, for example, if I start with an image is 227 by 227 by 3, my output should be like something like also 227 by 227, right? But let's say if I have like 10 different classes here, I should have an output like this, right? So and of course I can do something similar, but it won't work well as you go down this dimension here, and when you go up dimension, like you see like we didn't explain any tool here yet that can do like upsampling, right? So because all we did is downsampling, like the mass pooling is downsampling. When we do a filter, like a comp filter with stripe, for example, larger than 1, also is downsampling, but we don't have an upsampling step here. So what we need, for example, for semantic segmentation, we need to have upsampling. So you see, like for those, and that for many problems, like if I have an output, also have a same dimension of the input, I will need upsampling besides downsampling. So okay, I will see like if I have time to talk about that. Like if not, then you if you're interested, you can ask me like in the future, or like you can take my other class, like maybe like next spring. But so anyway, here is I want to show you a demo for Torch here. So I am for Torch again, it's quite simple to install. Like you can install like just like directly in Jupyter. So or like in Python, like pit install like Torch and Torch Vision here. I don't know, somehow my GPU is not working now. I think like let's see. Yeah, it's okay. I need to restart my computer, but I don't need GPU for this demo here. It's okay. So here you see like okay, maybe just a few words like how this work here. So you play with NumPy a lot already. So that's one thing like I like PyTorch quite a bit. It's like it's very similar to NumPy. Like you can convert. So it has its object like it's known as tensor. So it's like basically it's a high dimensional object. So you can okay, it's like just like you can have like two-dimensional tensors, or like two-way tensors are basically matrix, three-way tensor, like three-dimensional objects and so on. And you can convert like NumPy array. So it's like similar to NumPy array. You can convert directly NumPy array to tensor, like just using the torch tensor command. And let's see. Oh, by the way, one command, maybe it's not just a remark, like if you don't know, it's like quite useful. Like that's a you can import inspect in Python, and then you can inspect get source. Then you can just pin the source of all any command in Python. So it's actually it's quite convenient if you want to see the source. And so, okay, let me just go directly to, let's see if any, okay, go to this Westlight. So it's not, okay, I say Westlight because I originally use Westlight, but like it doesn't necessarily to Westlight. So here, like, I have this torch vision, like that's models. So that's it, all lots of models are already available. So it, okay, another package maybe I should mention is Caffe. I guess it's less popular now. But it used to be very popular. This is like not some kind of not designed as a programming language, but instead like it tried to construct the network using a configuration file. Uh, yeah, I think like this is a little bit out of flavor now, but it was popular like several years ago. Like I think it's still reasonably popular, and Caffe has kind of like introduced something known as this model zoo. I guess it's like some kind of database that allow people to upload their models, and many of these where's my yeah many of these uh, packages, like for example, PyTorch, TensorFlow, and so on, like, is able to access to this model zoo and so on. And I believe like this is like eventually is connected to model zoo, but anyway, I'm not sure it's like or like it's safe in PyTorch anyway. So, but if I look at this model here, like if I list these models here, so you see like in the Torch Vision models package there, they have like this number of largest models already available. And I mentioned AlexNet, right? There's Google Net, and Inception is also like by Google, and Westlight is very popular by Microsoft, um, and so on and so forth. Westlight is like yeah, very important, even though like it's a bit dated now, but it's like uh, it's still like one of it's a state of the art. So now let's try to just use AlexNet. I will load AlexNet here. So I have the models, then I just load a p-train models here. And then if I have this model evaluator, you see like it's like just printing out the models here. So more or less you see it's a sequential model, like you have conv layer, you have the kernel size 11 by 11, and you remember the figure there. And the input layer is like, wait. Oh yeah, input is like three, channel number of channel is three. Uh, oh yeah, output, okay. Yeah, number of channel input is three, number of filter is 64, right? Kernel size is 11 by 11, strike 4, padding 2, yeah. So, and then I use value like as the activation function. Uh, and then I do a mass pooling, like, and then like a kernel size like 3, strike 2, uh, padding, zero dilation. I'm not sure what dilation mean honestly. So yeah, but yeah, okay, you can look at that. I'm not going to take that up now. So okay. Basically, this is a network, right? And the network is already pre-trained. Um, uh, that's also like this is like the some of this you see drop out. I'm not going to mention this, but this is some regularization technique uh, for training that will allow you to generalize the model better. So in the sense, I improve your generalization because uh, you if you have like uh, if your model is too complex and you don't have sufficient data, then you may have this so-called overfitting problem in machine learning. So you may have a very low training error, but your test error can be pretty bad. It's just like overfit. So meaning that like for example, like in a classic like problem of like fitting curve, like let's say if I have the data like this, or maybe this is a exaggerate too much. So maybe I have a data like this, right? If I need to fit a curve here, uh, this looks like maybe I put it here. This looks like something quadratic, right? But if I have the data, if the model is too complex, I may overfit the model trying to just make sure that I go for all these points here. Then I will get something uh, like this. But in reality, maybe like I really have the data. I say look like this because I my data is noisy. So my training data is noisy. So therefore, like overfitting may not benefit. Like you may have like the real a different color here. The real curve maybe as in this is like this way. So therefore, like my the ground truth may be just really like this. I can when I have overfitting, my performance actually can get worse. So this and dropout is a technique to avoid overfitting. And so and now here I just load an image here. Let's see, I just have pull several images from online here. I just put in the URL directly, and then I can use this PIL to copy. This one is the, you see I normalize the image somehow. So this is the contrast normalization step like we mentioned earlier. But typically this is done like automatically. So I have this image here, right? This is a doggy here that is normalized as crop and then into the same dimension as the training data. And also the contrast is normalized. And then the device here, my GPU is not running at the moment, so it's a CPU. So I move them. If I have a GPU, then I basically in PyTorch, it's very easy to work on GPU and CPU, but you need to put everything either in GPU or in CPU. You cannot multiply a matrix in GPU and with a matrix in CPU. So you need to put both of them to the same device first. So here, I move into device here. If I, so into GPU here, if I have GPU running at the moment, but it's not. So, and then I have the batch here. So no gradient is not doing back propagation because I'm doing evaluation, right? I don't care about back propagation. So I have, earlier I already formed the image into a batch here. So, and then I put that batch also into a device and so that I can process by the model. So here, this step already do the processing, and I have the output is here. So if I pin out the output, it's just a bunch of numbers here. Because this is actually the probabilities. Let's see. 1,000 probabilities here. I think I can check the dimension here again. Yeah, it should be 1,000 because this is a image that the data is trained by the image that data set that's like 1,000 classes. So this is just the estimated probabilities for that 1,000 classes. And I can download this image labels. I already downloaded that. Exactly. See if I have it here. Oh, I should just close this. I just come up every time maybe I move to here. If you remember, I showed you guys last time also, what was that? Let's say image-led class, yes. This is the label of the 1,000 classes here. You see I have all kinds of stuff, right? Spiders, rocky, beauty, whatever. And then I open this classes here. Essentially here is just I pin out the top 5, right? The probability with the labels of the top 5 probability. So it kind of classify pretty accurately to how to call it, how to Labrador, I guess a retriever. Anyway, it's a retriever, right? We can try another image, I guess. Maybe try one more. I forgot what I put in. I just randomly pick one. So let's see what image is that. Okay, that's a another donkey here. It's a Pomeranian. So it basically did a really good job. Like all these data sets did a very good job for this uh, classes here. But it doesn't really do so well for, I think I have like one, if you look for classes that is not belong to this one, that may not do that well. But yeah. So maybe one more thing, like just to mention, like so that's something known as Tensorboard that is originally developed by TensorFlow, but PyTorch can also use that. So here, as you can see, like I can import like TensorBoard import like a summary writer. Then I can write the model here. I will AlexNet here, right? Then add the model, like input batch, right, to that device and so on. I close that. Then once I did that here, so I can run TensorBoard here. Oh, where is that? So it's a on 6006. Let's see. So it has lots of functionality, but like I like the way that like you can do very simple visualization of your lecture itself, because I now, yeah, you see I have an input, AlexNet model here, right? I can click inside that and double click to see, okay, precisely what it have. Like, okay, I have a sequential. So, and then you see like, okay, this sequential here is doing this like conf. If you remember earlier, we have also like that conf, and then we load conf and mass pooling, and then so on and so forth, right? And then uh, uh, I have okay, anyway, I have adaptive FH pooling here. I think this is a probably uh, the fully connected layer at the end. Yes. So that's basically it. So I still have 10 minutes. So maybe then I will explain one more thing. So as I mentioned, like if I want to do, for example, like semantic segmentation, like this one, I need to have the output dimension is the same as the input dimension, right? But if you remember the letter we have earlier, like we usually have like continue to downsample. Of course, like one way is like we don't do downsample, keep doing the same dimension as before. But typically this is a bit too expensive. Like this is not the most preferable solution. So instead, like what we can do is that we do this downsampling, but we need to do upsampling again. So when we do upsampling here, we need to figure out a way to do upsampling, because that's we don't have, when we do mass pooling, as I mentioned, and also convolution, there is both of them are downsampling. So maybe I just mentioned one upsampling step here. This is known as the transpose convolution. It's a essentially it's like if you think of convolution, it's like if you think of it as a matrix multiplication by the input there, then the transconvolution is, it can be mathematically written as like the transpose multiplied by the transpose of that matrix. So therefore, it gives this name like transpose convolution. But intuitively, it's very simple. So for example, if I have a filter, let's see, let's say if I have like start with like a filter, I have like 3 by 3. If I do a strike 2 here, originally I would be like this guy here, or also like let's say if I have padding here, like I have a one like padding with 1 here, so I with that start with like this one and compute the inner product with this patch, and then I got this one, right? And then maybe like this one got inner product, get this one, and so on. Like if I do strike 2, now if I want to do an inverse operation for that, of course I lots of information of that, but one reasonable way for me to do that would be simply I have this coefficient, and I will multiply by this kernel here and put it here, right? So for example, like let's say if I have this value here, it's a 1, 2, 3, 4, and if I have a kernel, it's a 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say like that. Then what I'm going to do is say, if I have this one, if I want to do an opposite operation, like kind of like semi, it's not completely inverse operation, will be like, I will just have this multiplied by the kernel and put it here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And then do the same thing like for this one, multiply by this kernel. Then I have like I pick a difficult 2, 6, oh sorry, 2, 4, 6, 8, 10, 12, 14, 16, 18, something like this, right? And then like, of course, there's some overlap here. So what we can do is I just add them together, right? So therefore, like this will become 5 here, and this will become like 14 here. This become like 20 here. And I can do the same thing also here, and then I will add this guy here. So then this will allow me to, from like a smaller resolution, go back up to like a higher resolution. And then with this step, like I can do like upsampling as well. Then I can train the model that have like this shape here. And then like again, you can do train end to end. Like for example, like for given this one, I know this would be like this. I can define an error for that one, and then I just minimize the loss basically. Yeah, that would be okay. I guess I have um, still some minutes here. So then maybe I should also mention the mass pooling. You can also do the same thing here, right? If you have mass pooling, you can do a mass unpooling here. For example, if I pooling like 5, 6, 7, 8 here, I can unpool. Then in the sense unpool, I can do it several different ways. One way is if I when I try to like unpool that, I may have like 1, 2, 3, 4. I may have this one like put in like both all the values here. I mean, put all the values in this region here, right? So, but a more popular way to do it is like, since we have this pooling and pooling step is usually occur in pair. So it usually is more beneficial. It's like you will also take advantage of the information when you did when you obtain like doing pooling. So for example, like during the pooling step here, we know the maximum like for these 4 guys is this one here at this location here. So during unpooling, we'll ignore all the rest, but I will just fill this one with non-zero, with 2 here, and so on and so forth, like for this guy also here, because this is the maximum during the pooling step. During pooling, I would just say put 4 here and not the rest of the node there. Yeah. So okay, I guess I kind of explain this. So maybe maybe just give a one-dimensional example, see if you guys actually understood what we talked about just now. So let's say if I have a 4x1 filter, right? So now let's do 1D here. And I do a strike 2, have a filter, 1, 2, 3. Then I will, okay, let me just say, okay, let's say I do a strike 2, and padding, I do 1. Padding 1, strike 2. So then I should get something like I pad a 0 here first, right? I'm 0 here first, right? So then you see, like, I will start with like this center at this like element here. Then skip 2, I can center at this one here, right? And I cannot do this one because I don't have like enough. So then the dimension I should get back is like just 2, right? I should have like 2 units here. So let's say if like strike 2 and padding 1, and this one is like this one here is the kernel. Let's say if I have 1, 2 here. So if I go back to have this convolution here, transpose convolution here. So what will be the output? This is the kernel. This is the input. Let's say 1, 2 here. Okay, is the question here? So I have the kernel. This is the kernel. And the setup here is I have strike 2 and padding is 1 here. And the input here, am I trying to do a transpose, a 1D transpose convolution? So what will be the output? Oops, I'm not sure. Like anyone's are still here actually. Yeah. We have 3 people are still here, I guess. 4, that's nice. So it's very simple actually. If you okay, I guess I would just say do it myself, but yeah. So yeah, it's basically as I mentioned, right? So you have like you just feel okay, I will have this one here at this location here. I will put up a filter 1, 2, this multiplied by this kernel here. So I have like 1, 2, 3 here. Then I should strike 2. I should skip 2 steps here. So I have the center set. Now I skip 2 steps here. I will skip to here. Then again, like this one multiplied by this one here. So it will be like 2, 4, 6 here. So I have the entire one will become like 1, 2, 5, 4, 6. Now, but know that like I have padding 1, right? So therefore I should remove this one and this one. So the output will be like 256, 254. Okay, one thing that you should be careful, therefore, is like I may not have the exactly the same dimension as before. So I start with the dimension, say 4 by 1, right? But I end up with like the dimension 3 by 1. So if you try to implement this thing yourself, like you have to be careful. Like even though like your pattern is the same, uh, you're trying to do transpose convolution, to do upsampling, hoping to get the same dimension as before, but it may not. So, okay, I will kind of, okay, actually, for you guys are still here, so I am sorry, like a little bit. Actually, I would like to give an advertisement or like wrap up the whole thing, but like I see like I did like actually I spend a bit time on that question here. So the thing is like we have this course, of course, is about computation, and you see like by now you see that like it's very much related to AI and so on. And of course, deep learning is as I mentioned, neural network is a very important technique now, and it's covered more in depth. Like in my another course will be like next spring, but I have another course I come interested in fall will be on some of you have already taken that course. So it's like in information theory and probabilistic programming. So it's more like on basic stuff, like in probabilistic models. So if you think of like AI is like really have few pillars in AI. Like one is like symbolic model, like expert system. Like I'm not sure it's like considered AI, but like symbolic models, like uh yeah, that's not in my I don't study that. But another two is like neural networks and probabilistic models. So for my class in fall, like we'll basically look more into the probabilistic models there. And so it yeah, okay, I guess I would just say, yeah, I guess okay. Hopefully we'll see you guys in the future anyway. So and good luck with your finals. And I guess that's it. And if you have any questions, I just send me uh, anything like for Discord. Yeah. So I'll see you guys like in future classes. Yeah. So see you guys. Thank you all. Bye.